Good morning and welcome to the second lecture of the course CP 4280, Introduction to CFD. Yesterday we started with the introduction and giving you a physical classification of partial differential equations in fluid dynamics. Before we continue, I would like to bring to your attention what we discussed yesterday regarding the first or the lessons on Monday. We got very quick response and we got actually a time, a room for the time that most of you, was possible for most of you, that is 12:15 to 14 hours in K26, that is in the chemistry building, the Alpha building. But still, there were a couple of people for whom this time was not appropriate. You have one, and are there others? Yes. Okay. So it's still for you not possible? No. Okay. So in that case, we'll have then two lessons on Mondays. This one and the one that we originally had scheduled from 18 to 20 hours. And that will be here in H1. So that will be then two lessons on Mondays, and the lesson on Tuesdays is from 16:15 to 18 hours. Do we have any questions regarding the organization, especially regarding the lessons? Okay, so then this will be the first occasion on Monday. And you have already the new exercise, the exercise 1 out, and you can and you're supposed to hand in that by Wednesday. So there's little time, but I think that will be not a problem, especially with the help that we want to give you on Monday and Tuesday. So you find that here in the exercise, and there is also some other thing that you might be interesting to you, and that is what Jürgen is doing here, taking a video of the lectures. So you can look there and see if you missed anything, you can look there and have the information there. And I'm grateful for any feedback from your side. I want to establish a reference group next week because I know some people will only arrive next week. So, but already before and independent of the reference group, you're very welcome to give me feedback, also to Reda or to Jürgen or to Alexander. Okay, so now let us continue, and the point now will be the mathematical classification of partial differential equations. So I think we don't need it any longer here. Regarding this, well, I'll write down the type of equation that we want to look at. We're going to look at second order equations of the type where we can classify the weight equation, the diffusion equation, and the heat equation. So then I have a question to you regarding your mathematical background on that from the math course. So that is now mathematical classification, and that is of PDEs. And we consider in the discussion second order PDEs, or second order PDE, in two dimensions. And the dimension may not also be time. And the order, you might remember from the math course, is always determined by the highest derivatives in the PDE. In that case, the PDE looks like that. We have, in the simplest case, just a constant. We can relax this condition a little bit. And then we have second derivatives of phi with respect to x. I define that shortly. This notation, it is a short term notation, also used in the book. Then we have another coefficient b times the mixed derivative. So the phi dx dy, I'll define that shortly. And c, another coefficient times phi yy. And that is equal to some right-hand side that we call h. And the h, can you see that? Can you see up here? So where the h, that is the right-hand side on this equation, is equal to, say, d phi x, another coefficient, times the first derivative of the dependent variable phi plus e phi y plus f times phi plus, and that is also a coefficient, and g. And these coefficients are, in the simplest case, constant. With constant coefficients it is a to g. We can also relax that. Coefficients can also depend on x and y. We want at the moment avoid that they can depend on phi itself, then it will be nonlinear. And regarding the notation that I promised, it's easiest to define it for the mixed derivative. Phi xx is then denoting the y derivative of d phi dx. So we take first the x derivative, d phi dx, and then of that we take the y derivative. And if we can also write that in the form d squared y, and then we have dy dx. We can also interchange that if the function phi is smooth, that is 2 times continuously differentiable. So, my question now to you is, have you seen this mathematical classification in your math course? Starting from that. Some yes, some no, yes. Okay. So it seems a little bit mixed. Well, my suggestion is, for those who have seen it, it's a repetition, and for the others it's then something new. Maybe we can, while I do it, at some point, I ask you again, and then we can decide if we do it in all detail or just give you the main points. But I think it's interesting because it shows some mathematical concept that how we can attack PDEs. So the idea is here, we want to find curves of C in what we are working is the xy plane. We are in 2 dimensions, and on these curves we want to see on which the second derivatives that we have of our independent variable or of our dependent variable, and there are phi xx, phi xy, and phi yy, may be discontinuous, so that they have a special property on these curves. And these curves are really important. We have already seen them when we discussed the wave equation. So those curves are called characteristics. They are particularly important for hyperbolic problems. So what we imagine now that we have the xy plane, and say we have the 0 defined here, and that we have some curve, say let's in the simplest case it would just be a straight line, but it can also be curved, whatever. That is our say one curve C. And what we want to do is we want to define a variable in this curve. That is, we call tau. So tau, say we start here at 0, it's varying in this direction. And then we can identify, say if we have a point here, we can identify that by, if we have for example here a tau 1, we have gone from 0 to here, then we can identify on the x-axis the corresponding tau, x of tau 1, tau y1, and here a y of tau 1. So we can then have a relation between, we can express the curve then as the vector xy of tau. So that's a parameter, the tau. And what we now do, we define quantities for the derivatives. So we shall use now this equation, this PDE 3.1. So we define on this such a curve C the following parameters. First we define the first derivatives. That is phi, sorry, it's not x, it's tau, because we are on the curve now. That is phi x. Then we have q of tau. We define that as phi y. So it means d phi dx and d phi dy are then called p and q. And u of tau is now phi xx. v of tau is the mixed derivative, and w of tau is the phi y1. So then we have a relation between these, and we now make an assumption. We make the assumption that we know the first derivatives and the function itself on the curve. We might know that from initial or boundary conditions. So that's now an assumption. So we assume that phi, our dependent variable, the x derivative of it, which is p, and q, the y derivative, that they are known, or that they are given on the curve. For example, as I use this acronym, this abbreviation for initial condition, or BC, I use that as boundary condition. So then, using the abbreviations that we have introduced, we can write equation 3.1 in the following way. So 3.1 becomes then, with this abbreviation, 3.2. That is, we introduce now the, what we have here for phi xx, the u tau, v tau, and the w of tau. So we get u of tau plus v of tau plus w c w of tau is equal to h. And with this assumption that we know phi and its first derivatives, we know h. You see that here. Phi x by y, we know because the coefficients are given. So then we have one equation. We are interested to determine these three coefficients, these let's see, we are interested to determine these u, v, and w, for which we may have a discontinuity in them. So what can we do to get that? We can now find a relation also for the derivative of the first derivative of phi x, and also of phi y along the curve C. So the mathematical tool is the chain rule. With the chain rule, we get, and that is then the following. We look at dp, that is the first derivative, and we do it now in the form that we say, we assume that we are on the curve, and we write now the dependence on x, but x is on the curve, so it is the x of tau and the y of tau. So that we want to take a derivative, so we want to take a derivative along the curve by that. So then we can use the chain rule, because now the arguments, p depends on the arguments, and the arguments depend on the parameter tau along the curve C. So we get the dp dx, and then dx d tau, plus the dp dy d tau. And now we can use what we had before. We can see that this here, the dp dx, that is then the phi xx. And the dp dy, that is the phi xy. And this we have introduced the acronym U, the abbreviation U, and this is the V. So from that we get then a relation of the derivative of P, we call that 3.3, that dP d tau is equal to U dx d tau plus V dy d tau. So then we have a relation between the derivative of P and the unknowns U and V. And similarly we do that for the derivative of Q with respect to Y. Similarly, we get the derivative Q, again on the curve, then it is an x of tau and y of tau. The derivative, again with the chain rule, is now dq dx d tau plus the dq dy dy. Now we use the abbreviation that we have introduced. This is the phi y with respect to x. So then we have here the phi xy. No, it is actually, if we are picky, then it is in this order. Here we assume that this is continuous so that we can revert it. So we assume that we will assume that we can write this way. And then we have here dx d tau plus, and the dq dy, that is then the phi yy. dy tau. And that we have given the name v, so that's v, and that was w. So from that we get then the relation which we call 3.4, that dq d tau, the derivative of phi y along the curve, is equal to v dx d tau plus w dy d tau. So now we have three equations. It is this one, and it is the original PDE that we have here, and it is this one. So then we can express that as a linear system. So then we do that. So the equations 3.2, 3.3, and 3.4 constitute a linear system. For our second derivatives, u, v, and w on the curve C. And in matrix form, we can write that then in the following way. So what we want, we have here a matrix. Here we have our unknowns. The unknowns are u, v, and w. And we have some right-hand side. So then we have to translate these three equations. Here we have 3.2 and 3.3 and 4 into this matrix form. So how do we do that? That's matrix operation. So we have A, B, and C. So they will come in the first row. A, B, and C. Then you see, if we do the matrix vector operation, we'll have A, U, plus B, B, plus C, W. That's exactly what we have on the left-hand side of this equation. So the right-hand side then will be H. Second equation we get from this one here. So now we have the coefficient on u is dx d tau, and on v dy d tau. We have nothing on w. So that means we get here then dx d tau, and here we get dy d tau, and we get 0. If you do this operation, we get the left-hand side on 3.3. The right-hand side is dt d tau. So, and now is the last equation left. We have it here. We have nothing operating on u, so we have only dx d tau operating on b and dy d tau operating on w. So that gives us then the following. We get 0 dx d tau, dy d tau. And the right-hand side is dq d tau. So then we have this linear system. So we can express that here. That would be the matrix A, that would be our unknown x, and that would be our right-hand side B. So it's a simple 3 by 3 system. now the starting point was to find second derivatives, or to find a curve on which the second derivatives might be discontinuous. And what we do now, we look for a condition when this linear system might be non-unique. If the determinant of A is not 0, we can directly get the solution and it is unique. But if the determinant of A is 0, then we might have a non-unique solution. So that will be our condition. So if the determinant of the matrix A is 0, there may be a non-unique solution. And that we take as a condition that we are non-unique or discontinuous, in this case on the curve C. So therefore we take the determinant of A equal to 0. That is then equivalent to saying, well, we have then to determine the determinant. Well, you know the rule is, go along this line, we get A times dy d tau. Here we get a 0, and here we get C, and we get second so dx d tau 2 times. So we get then the following. We started with the A, that is the dy d tau squared, and the one that is missing is then this one is 0, and this one is 0, but we get dy d tau b dx, dy d tau b dx d tau. So that is coming with a minus. And then we get dx d tau squared is equal to 0. So that we take now as a condition when we might have non-uniqueness or a discontinuous solution for u, v, and w. And this gives us now a way to determine this curve, because we have here relations between dy and dx. What we can do now is we can divide this equation by dx d tau squared. Nobody hinders us with that. So that means we can get from that A dy dx squared minus b dy dx, because dx dy, this one goes and this one gives them dy dx, and here we have then c and nothing more. And now we can introduce the slope of the curve C. Slope of the curve C. And that means we say pull at h dy dx. So then we can simply replace that with the h. So then we get here an h squared. Here we get h, and we have a second order equation. So that means we get from that then that we call the 3 point. Let's see, did I give that? Well, I think I forgot to give this a name here. 3.5, this first condition here. Then the 3.6 then is then coming directly from here, h squared plus minus bh plus c is equal to 0. So that's the second order equation for which we can find the solution easily. So the solutions of this equation 3.6 are, and we might have two solutions. H, which we remember is defined as dy dx, that is the slope of our curve C, is equal, then it is the formula to solve second order equations, which is b plus minus square root of the discriminant, which is b squared minus 4ac divided by 2a. So that will give us the slope of the curve C. And now we can define the characteristics. The curves y of x with slope, or back to we have the slopes 3.7, like this. They are the characteristics. They are the characteristics of the second order PDE that we started with. 3.1. Okay. So for those of you who have seen it before, is this a different way to see it, or? Okay. But from this point on, we can now classify the PDEs, because depending on the discriminant, we have either two solutions. If this is b squared minus 4ac is greater than 0. If it's 0, we have just one solution. And if this is negative, we have no real solution. In these three cases, determine then whether the PDE is hyperbolic, parabolic, or elliptic. So then we have a classification. So let me write that. So, the discriminant which is b squared minus 4ac determines whether we have 2, 1, or 0 solutions. So now we can do the classification. If the discriminant b squared minus 4ac is greater than 0, we have two solutions. So then we have two slopes, so we can define the two families of characteristics. And the PDE 3.1 is called hyperbolic. And that is the case that we discussed yesterday with the wave equation, where we saw already with the physical classification. On these two lines are the characteristics. In that case, they have the slope plus and minus speed of sound. And if we do the analysis, then we'll see it comes out by this. If the discriminant is equal to 0, we have one solution. We'll discuss all the solution here for H. And then the PDE 3.1 is called parabolic. And in that case, say we had before, we had the characteristics for the hyperbolic case. Let's see, maybe we can illustrate that. So we had the case, and in the hyperbolic case, then we will have x and t actually. So t takes the row that was given to y in the discussion here. So then we have two characteristics. So here that was what we discussed yesterday. So this will be then we have this dx2 t is equal to c, and the dx1 of this is of t, dt is equal to minus. So they are then the characteristics. And in the case, so that is for hyperbolic case. And the case for the parabolic situation, for the diffusion equation or the heat equation, we would have a situation where C gets larger and larger, and as it goes very, very large, it becomes just a straight line. So that will be then the characteristic, so to speak, here. So that will be for the parabolic. So it's simply here, if we are at some time t1, for example, so again, this is t here, then we are up there. And that was what we discussed yesterday. Everything from here on can influence what is coming next. And everything that we have here is influenced what we have at the boundaries. We have boundaries here, and what we have at the initial case, in the initial condition. So then we have the third case left. And that is if d squared minus 4ac is smaller than 0, we have 0, and here I might add real solution. No, real solution. We have a solution, it would be complex, but that doesn't make sense. We cannot identify a curve with that. And in that case, the PDE 3.1 is called elliptic. So in that case, we cannot write a characteristic because they do not exist. So let's see. Well, these are conic sections with a plane. So we have a cone. Let's see. Now. So we have here a cone, 3 cases, and depending on how we do the cut, then we get different intersections on the cone. So we do an intersection of a plane with a cone. In this case here, we intersect, say, in a way that we just get one parabola. In this case, we intersect that we can get either a circle or an ellipse. See the two situations, you see a circle and an ellipse. But a circle can also be regarded as a special ellipse. So that's one part. And the right hand side we cut, and then we get 2 solutions, here and up there, hyperbola. And the analogy with that, with the conic sections, has given the name to these PDEs. Hyperbola, hyperbolic PDE, parabola, parabolic PDE, ellipse, elliptic PDE. Because in analytic geometry, these conic sections are governed by a very similar equation. It has exactly the form that we saw in the beginning, but instead of phi xx, we simply have x squared. So that's like that. So names that we use here come from analytic geometry. So conic sections, they can be written as a squared, sorry, a x squared plus b xy, or actually it's then if we would be, now this would be a minus, plus cy squared plus bx plus cy plus f is equal to 0. And they are called, and they are representing a hyperbola if b squared minus 4ac, that is exactly the discriminant that we also discussed, if that is greater than 0, then the conic section is a hyperbola. If that is equal to 0, let's see, I have to put that here in similar form, so we have a hyperbola, then we have a parabola, and if it is smaller than 0, then we have an ellipse. So on these, therefore, we have these names. Okay, so that, the point that is now interesting, but that I leave to you, is to, let's see, as a little exercise, classify 1D wave equation, the diffusion equation would also be the 1D diffusion equation, or heat equation would be similar, and the Poisson equation. Because they all are second order PDEs, and they all can be classified by what we discussed. Now, okay, so by that we have now a good classification of second order PDEs. Regarding first order PDEs, I want to skip that here. If you're interested, you can read that in the book. And we will also come back probably at some point later. Let me see. Maybe not, we will not come back to that. Because we can also classify systems of equations when we have, for example, du dt, where say we have say a vector v plus a matrix A times v dx equal to 0 or some value that is independent of v. So in that case, we can define also a hyperbolic system if this matrix A has real eigenvalues and linearly independent eigenvectors. So that is a classification for that. And we can also have a type of equation where we have dv dt is equal to, say, the matrix B times the second derivative of v with respect to x squared. And then we can define a parabolic system if the eigenvalues of b are strictly positive. So that is just a side remark. Probably we will not come back to that, but as I said, you can read about that in the book. So anyway, we have now a classification of PDEs, and as we saw with the discussion for the physical classification, this has different applications on where information is coming from and where it is going. So the domain of dependence and the domain of influence is different for all these three classes that we have: hyperbolic, parabolic, and elliptic. And the thing that we want to do after the break, which we'll then have 15 minutes break now, is to look into the sources of error in CFD. And that will give you then the material to do exercise 1. Okay, so we stop here and have now 15 minutes break.